And then, right. And then the meat of the talk will be this section 2, where I combine Monte Carlo inference and quasi-stationary distributions. And then in this final section is when I'll be talking about work I've been doing with Daniel Rudolf on perturbation theory in the context of quasi-stationary distributions. Then I have a very short conclusion at the end. And please do interrupt me at any time. I'm hoping to speak for only about 35 minutes, maybe a bit more. So please interrupt me at any time if something is unclear or you have a question or anything. Okay, so what is the kind of fundamental setting? Well, I'm coming from this perspective of Monte Carlo inference MCMC, where typically the kind of settings that we wish to compute some kind of integral numerically, because we could never do analytically in high dimensions. And so, for example, we wish to compute something like I, where you write the integrand as a function f against a probability density function pi. And this, still is not analytically tractable or anything. And so what you do then is you sample from pi. If you could do IID sampling, do that. You sample from pi and then appeal to some kind of law of large numbers to say, if you take an average, that should approximate your integral I. But of course, exact sampling from pi is incredibly difficult, except in very specific situations. And so instead, we settle for approximate sampling from pi using a stochastic process. To spell that out, what that means is you construct a Markov chain or Markov process from the ground up, which by construction will possess pi as its stationary distribution. So unlike kind of traditional probability theory, where you're given a stochastic process and derive its stationary distribution, here we're starting with a stationary distribution pi, and we build a Markov chain or Markov process, which is invariant with respect to pi. And so the kind of classic ways you might do this would be in discrete time using a Markov chain, probably using the Metropolis-Hastings algorithm or some variant thereof. Or you might work in continuous time and use a diffusion process, such as the Langevin diffusion, underdamped or overdamped. Or more recently, there's been interest even in using piecewise deterministic Markov processes. This is something I've also worked on, but I won't be discussing that in the talk today. And so you hope this Markov chain or Markov process that you've constructed is ergodic. And if so, essentially by definition of ergodicity, regardless of where you start, what your initial distribution mu is, if you run the process for long enough, you take a large t, then by ergodicity, the law at time t should approximate pi. And so what that means is you can approximate from pi straightforwardly by just iterating repeatedly the transition kernel pt. And so that's how we're going to get our approximate samples from pi. So that's kind of the traditional MCMC Markov chain Monte Carlo kind of setting. In this talk, I'm going to be interested actually in killed Markov processes. So we've seen quite a lot of these already today, but I'll just introduce my notation. So we're going to be on a state space curly x, and a Markov process xt in continuous time will be killed if there's an almost surely finite stopping time, tau d, at which point at tau d, this particle is instantaneously sent to some cemetery state d, which is not in the state space. And because this absorbing cemetery state is not in the state space, it means, the total mass of the state space x is going to be typically less than 1, because there's some probability you've been killed. And so in this context, then I'll call a probability distribution pi on x a quasi-stationary distribution when you're initialized in pi, and you consider the condition dynamics conditioned on non-absorption at time t, if this condition law is still pi, and this has to be valid for all times. And so, of course, if you got rid of this conditioning, this would just be a standard stationary distribution. But because we're in this killed Markov process setting, we condition on survival, and then we ask that this conditional law equals pi. And this is closely related to what I'm going to call a quasi-limiting distribution. So some people might call this a Yaglom limit, but I'll refer to it as a quasi-limiting distribution, which means for any initial point fixed x, these condition laws, when you start at x, will get absorbed to pi when you take t large enough and consider these condition dynamics. And when you're in this killed Markov setting, these two notions aren't exactly the same, but they're very closely related. But I won't go into those subtleties here. So these are my definitions of quasi-stationary and quasi-limiting respectively. So let me just give a really simple animation. So this is the unit disk, or maybe it's not the unit disk, but it's a disk in the plane. And I think there are 5 processes here. We're just undergoing a Brownian motion with what you can call hard killing at the boundary. So you see that these processes, some of them hit the boundary and they're instantaneously killed when they hit the boundary. A silly story I sometimes tell is you can imagine that these, say, were ants which are stuck on a volcanic island, which is surrounded by lava, and the poor ants are instantly incinerated as soon as they touch the lava. And you'll notice though that among these, 6 trajectories, there was one ant which happened to survive by pure luck up to, I think, stochastic process time 5. And its final location was this green point here. So of course, because it happened to survive for time 5, the law at this green point is not the law of a Brownian motion at time 5 anymore, but it's the law of a Brownian motion conditioned on not touching the boundary of this disk. And you can imagine if you conditioned survival for a very, very long time, it would probably forget where it started, which maybe was the center, and that would in fact be the quasi-limiting distribution. So this is an example of what you might term hard killing, just like in the kind of neutron transport situation. This is like killed when your particle hits the boundary of the reactor, for example. It's just instantaneously absorbed, and that's the end of the story. In my kind of MCMC applications, though, we're not so interested in kind of hard killing where there is some boundary which instantaneously absorbs you, but we're interested in situations where you could be absorbed from anywhere. And so I'm going to define a killing rate, which is a function from your state space into the non-negative half line. And the corresponding killing time is now given by the first time at which this accumulated hazard, if you like, exceeds the random threshold C, which is an exponential 1 random variable. And so this definition of tau d is entirely analogous to the kind of scattering or fission times we've seen many times today. The key difference here is that this XS process is, in my case, a diffusion rather than just a kind of linear transport with some bounces. But otherwise, it's an entirely analogous definition. So now here's going to be another really simple animation, except of soft killing rather than hard killing. So once again, we have just Brownian motions in the plane, but they're being killed at a quadratic rate. So the killing rate is something like just norm y squared in the plane. And so you can see there are 2 trajectories which started a bit further away from the origin, and they did not last very long. And on the other hand, there are some other trajectories which lasted a bit longer. I think a few of them will die fairly soon. Or maybe I'll just skip to the end. Right, and so you can see there are several trajectories, and kind of when they strayed too far from the origin, unsurprisingly, they got killed off. But there was one trajectory which, again, just by luck, managed to survive, I think, for 5 units of stochastic process time. And so once again, this green dot, the final location, is no longer the law of a Brownian motion at time 5, but it's this conditioned law, conditioned on non-absorption up to time 5. And as we all know, Brownian motion, if you just leave it to its own devices, is neighborhood recurrent, it just explodes everywhere in the plane. But of course, if you introduce killing at some rate, say norm y squared, and then condition on survival, what you've effectively done is you've imposed a kind of stability on the remaining sample paths, right? The paths which will survive until time 5 are probably ones which did not stray too far from the origin, otherwise they would have died. And so we've kind of forced a kind of stability on this diffusion process, which wasn't there before. And that's exactly going to be the kind of idea behind quasi-stationary Monte Carlo methods, where we're going to try and use this killing and a kind of conditioning mechanism to force the particle to go into a distribution which we choose. And so in this particular example, with a quadratic killing rate, it's intimately connected to the harmonic oscillator. And so you probably can guess that the quasi-stationary distribution here is just an isotropic Gaussian distribution. And that's quite straightforward to show, and we'll see that later. So this here is the kind of soft killing situation we'll be interested in. But of course, we're not interested in sampling from Gaussian distributions. We're interested in some general target distribution, maybe from Bayesian inference. And so the first question would be, can we hand construct a killing rate which would lead to our target distribution pi being the quasi-stationary distribution? And so let me just spell that out a bit more. So we're all familiar with stationary distributions from our first course on Markov chains or Markov processes. But in my talk today, we're interested, rather than looking at stationary distributions, constructing a kill diffusion whose quasi-stationary distribution coincides with a given target. And so then the related computational task is, how then do you sample from pi when pi is the quasi-stationary distribution of a killed Markov process? So I hope the kind of motivation is there. Okay, but why on earth would you want to do this in the first place? I mean, what's wrong with just bog standard MCMC? So the kind of motivation for using this killed Markov process framework is essentially to perform exact Bayesian inference on tool data sets. So in Bayesian inference, the goal is to sample from a posterior distribution, which is typically of the following form, where you have, say, a prior term and then a likelihood term. And so this is a fairly general form. This is not necessarily assuming IID data, because, for example, the FIs could be kind of conditional on all the previous ones. Whatever, it doesn't matter. We have a kind of product form of our target distribution. In a kind of tool data setting, what that means is a number of observations n is incredibly large. So that the reason it's called tool data is because we imagine that if you're doing, say, you had your covariate matrix X, it's a very tall matrix. It has a really large number of rows because we have so many observations, but it's not too high dimensional. So it's tall in that sense. And if you have such a posterior distribution where n is particularly large, standard metropolis Hastings is incredibly inefficient because at every single Markov chain iteration, you have to evaluate the target distribution when you construct your acceptance probabilities. And if n is particularly large, pointwise evaluation of pi is, of course, an order n computation, which can be a huge burden if, for example, your data set is so large, it can't even be stored on a single computer. You do not want to be looping over the entire data set at every iteration. And so the natural question is, well, can we do some kind of workaround and just work with maybe a small subset, a subsample of the data, rather than all of it? But the problem is kind of your very simple, naive workarounds, for instance, just throwing away most of the data and only looking at a tiny subset, will typically incur some kind of asymptotic bias, meaning that they'll fail to recover the true pi, even when you run your Markov chain for an arbitrarily long time. And so that's, of course, not great. I mean, sometimes you accept that and that's fine, but it's not always great. On the other hand, using this quasi-stationary framework I'm going to present, it allows for the principal use of subsampling. And in the machine learning literature, this is often referred to as stochastic gradients. The idea being, rather than using the full data set, we are genuinely just going to use a tiny, like mini batch, a tiny subsample, which will be order 1. And the reason you can do this on a very high level is because in this quasi-stationary Monte Carlo framework, you end up requiring unbiased estimates of log pi. And of course, remember, pi was a giant product, so log pi will be a giant sum, and unbiased estimates of giant sums are very easy to do because you could just, for example, take a uniform random index and just go with that. And of course, I've skipped a billion details. You can read about it in the original paper of Pollack et al., which was presented last year at the Royal Statistical Society, which kind of started this whole kind of quasi-stationary framework. Okay, so I hope I've given you some sense of why we're interested in this kill diffusion setting. So now let me spell out the kind of mathematical setting we'll be working in. So the underlying process, which is going to be killed, is a diffusion process living in Euclidean space. And the form we'll take is as follows. So this is a kind of reversible diffusion. If you like, you can just take A to be a 0, in which case it's just a Brownian motion, like in my animations. That's completely fine, but this is slightly more general. As before, killing is defined through a function which maps the Euclidean space into the non-negative half-line, with killing defined as before. And so, for example, in this kind of MTMT Bayesian inference setting, we will choose this kappa in such a way that the quasi-stationary distribution pi is exactly what we want it to be. It's our posterior distribution. And I won't go into the details of this result, but under mild regularity conditions, if you choose kappa as follows, which of course has some derivatives in it, and it depends on this drift A, then indeed pi will be the quasi-limiting distribution. And so, for example, if your A is 0, because you're working with the Brownian motion, the second and third terms disappear, and we just have a fairly simple term, which depends on the Laplacian of pi divided by pi. And so, for example, if you take A to be 0, and you take pi to be an isotropic Gaussian, you can just do this calculation, and you'll see that you exactly get norm x squared. So that's where, the first example came from. And this k at the end is just to ensure that this killing rate is non-negative. Because yes, so in all of the work I'm presenting, we do not have any particle creation. Particles only die, they're never going to be created out of thin air. And so that's why we need this rate to be non-negative. Okay, so suppose now we have done what I've just said. We've constructed a killed diffusion whose quasi-stationary distribution is exactly what we want to sample from. And so the question is, how do we sample from it? So in my kind of motivating MCMC examples, we knew by construction that xn converged to pi in distribution. And so what that means is you can just repeatedly apply this transition operator p to approximate pi, right? That's what we know in the MCMC setting. But in this kill diffusion setting, the analogous statement would be this quasi-limiting property I mentioned towards the start of the talk, where your condition dynamics are being absorbed to pi. But this does not immediately give a useful algorithm, because this would suggest you do some kind of naive rejection sampling where you just draw trajectories until you finally get one that's survived for some large t, and then you take the final point there. But the problem is these probabilities are decaying exponentially with t. And so if you want to get a reasonable accurate estimate of pi, you need to take t to be large, which would be impossible to do with any efficiency. And so, of course, that's not what you're going to do. Right, so indeed, we're interested in some kind of sensible Monte Carlo algorithm to sample from this quasi-stationary distribution. And in the context of Bayesian inference, this is what I'm calling quasi-stationary Monte Carlo, QSMC. Okay, so the first reasonable approach to do this, which is what was done in the original scale paper, which I mentioned, is to use a kind of interacting particle system, which is essentially a continuous time sequential Monte Carlo approach, which is exactly like what Pierre Delmoral presented this morning in his talk. And indeed, his work with Lauren Miklo is one of the original kind of works that did this, but also Birdsey et al. From 2000. I'm not going to go into the details of this, but at a very high level, you are running just essentially a cloud of particles which are being killed. When one of them gets killed, it's reborn from the cloud. So you pick up one of the other locations, you go with a winner. I like Pierre's way of calling it. And you just run this cloud of particles for a long time. And that will, at the end of the time, approximate the quasi-stationary distribution. So this, because you're running a kind of cloud of particles, it's like you're doing sampling in space, because at the end of the day, you're going to take a weighted average of your spatial positions. So this is one approach which you can do, and it's what was done in this Pollock et al. Paper. Alternatively, though, you could do a different approach. Rather than sampling in space, you could sample in time. And that's what I'm going to focus on in this part of the talk. So this is instead using a stochastic approximation approach. So the idea here is, rather than running a kind of cloud of particles which are interacting, you run a single killed particle forwards in time. And when it's killed, you don't just stop there, but you look at all of the places the particle has been up to that point, pick a point for its trajectory, say uniformly at random, and then just restart the process at that point, run it forwards in time until it's killed again. And each time it's reborn from its own empirical occupation measure. And there are a few tweaks you can do to this, but I won't go into that. And indeed, convergence of this algorithm I've just described has been proven in various settings. So as far as I'm aware, the oldest example is a paper of David Aldous and co-authors from 1988, who looked at discrete time finite state spaces. And since then, various people have looked at this problem, including me when I was a PhD student, and also Cécile Marie and Denis Villemonnet, who I believe are in the audience. I think Denis Villemonnet will be talking about this work, in fact, tomorrow. I think theirs is currently the most general result, where they even looked at some non-compact state spaces. So that's really nice. I think, oh, yeah, now I have another short animation just to show you kind of pictorially what's going on. So there's a single trajectory being run forwards in time. So this is a killed Brownian motion being killed at this quadratic rate. At some point, it will get killed off, I think, I hope. It's very lucky. There you go. So it was killed at this point, and it jumped to some point over here, which is drawn from its empirical occupation measure. And then it just continues to diffuse from there until it will get killed a second time, which will happen eventually. Some point over here. Okay, it got killed there, and then it jumped over here. So maybe I'll just skip straight to the end. So this is what, maybe 10 or so lifetimes. And as you can see, whenever it strayed too far from the origin, that's when the killing was high. It tends to get killed off. And at each time it was reborn from some green point chosen uniformly at random from its history. And yeah, of course, you hope if you run this long enough, you will indeed converge to the quasi-stationary distribution. Right. And so in the context of kind of exact Bayesian inference on RD on tool data sets, this algorithm we've dubbed regenerating scale, or rescale for short. And just to maybe state the obvious, which has probably occurred to you already, rescale, it differs substantially from traditional MCMC methods. For starters, it's not actually a Markov process unless you augment the state space, because it's a self-interacting diffusion, right? Clearly, this trajectory is interacting with its past, right? Because it goes to places it's visited. And so it's not a Markov process on its own. And so the way you analyze it is not by using kind of Mine and Tweedy and the standard Markov chain literature, but rather exactly using stochastic approximation approaches. As an algorithm, though, it's rejection-free, or they're kind of with a star, because when the particle is killed, that's a kind of rejection. And it's also amenable to subsampling, the stochastic gradient thing I talked about to deal with tool data. And just to say, a rigorous proof of convergence on RD with Brownian motion is actually still an open problem. So perhaps Denis Villemonnet will talk more about this tomorrow, but yeah, people who are looking for a challenge, this is something I've not been tried to solve, but not been able to. So now let me just give a couple more pictures. So Divakar Kumar, who is a student of Garrett's, indeed applied rescale to various problems. And so this is just a two-dimensional example just to show you what it looks like. If you imagine I ran my animation for a lot longer, you'd build up a picture like this, where if you can make out the colors, the red points, as expected, tend to be on the outside, and the green points are kind of scattered across the distribution according to the quasi-stationary distribution, in fact. And just to show, Divakar did also indeed apply it to some genuinely tall data sets. So this US domestic airline data set, I think, has n equals 120 million or something or other, which you would not want to touch at every iteration. And indeed, he was able to get reasonable results for logistic regression on this data set. Okay, great. So that was kind of what we've now been calling vanilla rescale, where you just run the process and whenever it's killed, you look at its empirical occupation measure. Up to now, I've entirely kind of swept under the rug the question of how you actually sample from this empirical occupation measure. Because of course, when you're looking at a brand new motion, its trajectory is an infinite dimensional object. Of course, in my animations, I just discretize time very finely to produce the animations. But if you actually wanted to sample from this object, to do it exactly is highly non-trivial because you cannot store the path. And so the way Divakar does it is using some very clever tricks based on diffusion bridges and lookup tables, which allows you to do it exactly, but it's really quite expensive. And in fact, it's an order T calculation. So the longer you run the algorithm for, the more expensive it becomes to do this. And so this is the key bottleneck that really impedes the efficiency of rescale. And so a natural question you might ask is, one, that is incredibly complicated and incredibly expensive. Could we do some kind of approximation? Right, we'd like to sample from mu-t, but we really don't want to. Could we draw instead from some mu-tilde-t and cross our fingers and hope that if mu-tilde-t is close enough to mu-t, we still get an exact algorithm? And so, for example, a fairly natural approximation of mu-t would be, rather than this full infinite dimensional object, you take a kind of finite dimensional summary. So rather than looking at the entire trajectory, you just pick a finite set of points, which you hope are in some sense representative. And when you draw from mu-tilde-t, you just pick from this finite set and just work with that, which is clearly an order 1 cost calculation in terms of t. And so how might you pick this representative set? Well, one way you might do it is, as you're running forwards in time, you have an additional homogeneous Poisson process with, say, rate 1. And whenever that clock rings, that's when you record the location at the time, which you can certainly do with almost no extra cost forwards in time. And so if you do this, this entirely circumvents the need for these really complex simulations involving diffusion bridges and all kinds of other complicated stuff. And I think, okay, yeah, I have time, so I'll go through this slide. And in fact, actually, if you do it carefully, this is still valid, actually. So in the proof of convergence of rescale, this is still valid, provided that these mu-tilde-t's, so this kind of atomic approximation, converges to the true mu-t at a polynomial rate. In other words, we want to show that this kind of finite dimensional summary of this full infinite dimensional object is close at a kind of polynomial rate in t. But actually, one of the reasons you might pick a Poisson process here is because, in fact, these xti's, once you've conditioned on n, are actually IID from mu-t. Right, this is just a kind of fundamental property of the Poisson process, which is saying, suppose you want to simulate a homogeneous Poisson process on, time interval 0, 10, say. What you could do is you could draw a Poisson random variable, which tells you how many arrivals you had until time 10. And once you fix that number, you just throw IID uniforms into the interval, and those will be the arrival times of your Poisson process. And so this is just using that fact to say that these xti's are actually drawn from this mu-t. And so now this problem falls exactly into the framework of empirical process theory, which is exactly about saying, when do these kind of empirical measures converge to the actual measure? And this gives you the kind of polynomial rate that we want. And so this is something neat which we're implementing at the moment. Right, so that's all I wanted to say about the stochastic approximation approach. If people had any questions at this point, I'm very happy to take them. Otherwise, I'm going to move on to talk about perturbation theory. Okay, so I'll talk about perturbation theory then. So this is joint work with Daniel Rudolf, who I think is in the audience, and this is very recent work. So we're hoping to archive the first version of the paper next week. So what is perturbation theory? So perturbation theory in general, it studies the stability of certain systems under small perturbations, where at the moment small is deliberately vague. And so, for example, in the context of Markov chain Monte Carlo and Bayesian inference, a question you might ask is that if you're running this Markov chain on your computer, but you actually perturbed it somehow. For example, maybe you don't have access to the true pi, but you have, say, missing data, right? You don't have access to the actual posterior, it's been corrupted in some sense. And so really you're running your MCMC algorithm with a slightly dodgy target, which is modified. Or maybe you're running stochastic gradients, so not the full gradients. So you're doing another approximation. Or maybe you're just worried about numerical errors in your machine precision, right? These are all things which will perturb your transition operator slightly. And the question you can ask is, well, does this affect the resulting posterior inference? It's an entirely reasonable question to ask. And in this kind of Markov chain setting, there is a well-developed literature which is typically bounding the distance between your true invariant distribution and the kind of perturbed invariant distribution, the invariant distribution of your perturbed chain, where D is some distance measure, typically either total variation or Wasserstein distance, something like that. And there's a lot of papers in this, so here's just a few representative examples. But yeah, this is a fairly mature literature, I'd say. And so the question we asked ourselves is, well, what can be said in the quasi-stationary distribution context, right? These results are great for Markov chains, which are unkilled and have stationary distributions. Can we say anything about perturbing, say, killed processes and their, associated quasi-stationary distributions? Can anything be said there? So to be concrete, as I have been saying throughout this talk, we're going to be working with killed reversible diffusions on Euclidean space, just to be concrete, with killing at some rate kappa. So it's soft killing rather than hard killing. And so in this typical quasi-stationary Monte Carlo setting, recall that the target distribution or the data only entered the system via the killing rate, because the underlying process was just, say, a Brownian motion, which knows nothing about our target distribution. All of the information of our actual target entered through this killing rate. And so, for example, if you had some kind of missing data or corrupted data, what would end up happening is that you'd be running with an alternative killing rate. You'd be running your killed Brownian motion with a kappa hat rather than the true kappa. And so on the kind of operator theory level, that corresponds to perturbing the generator by some perturbation H, which is simply the difference between the two killing rates. And this H is a multiplication operator, and so it's certainly an example of a self-adjoint operator. And so let me just remind us what I mean by these generators, what they are exactly. So remember, this underlying diffusion was this reversible diffusion. Again, take A to be 0 if you like, so it's just a Brownian motion. And the generator of this unkilled diffusion, I'll call L0F, which is a differential operator. Again, if it's Brownian motion, it's just the Laplacian. In this talk, I'm not going to go into the details of the domains. Of course, they're crucially important. We deal with that stuff in the paper. I won't bore you with those details right now. But these generators, they're unbounded operators, but they are self-adjoint. So this is good. And now we introduce the killing rate. And what does that do to the generator? Well, you add this extra term on the end, which is also self-adjoint. It's a multiplication operator. And this gives us the generator of the killed diffusion, L kappa. So it's L0 minus this extra term, which is the killing. So in terms of the, I guess it was the backwards equation we saw earlier, there's just a missing creation term here. We're just killing particles. When they're killed, they just leave the system, they're dead. They're not being created to compensate it, which is why mass is leaking away from the system. Okay, so given the generator of a killed diffusion with generator L kappa, which by construction has a quasi-stationary distribution pi. So here's L kappa again, just to remind you. We're going to consider now what happens when you take a general bounded self-adjoint perturbation H. So I'm going to make, for this section of the talk, the assumption that this perturbation H was in fact bounded. So in other words, that means the kind of the absolute value of the discrepancies is no greater than some fixed finite quantity. So we're assuming these are kind of small perturbations. If the data was corrupted beyond belief, well, there's no reason why it would still be valid. So assuming that the corruption is not too severe, we have a bounded perturbation. And so we can prove the following thing. So the crucial assumption we're going to make is that this L kappa possesses a spectral gap. And I'll say a few words about that in a moment. So we're assuming that at the bottom of the spectrum, we have the quasi-stationary distribution, and then there's some gap And then there's the rest of the spectrum, which could be continuous, discrete, whatever, but there is some spectral gap there at the bottom. Provided that's the case, we can find some delta, some positive constant, such that for any perturbation which is below delta in operator norm, there is in fact still a perturbed quasi-stationary distribution of this L hat operator. And in fact, we can bound the discrepancy between the corrupted quasi-stationary distribution and the true one by constant times the norm of this operator H for some constancy. And this norm here is in fact the L2 norm, because these are self-adjoint operators on an L2 space. So this is the L2 norm. Let me just say a few words about this assumption of a spectral gap here. So in practice, if you're doing quasi-stationary Monte Carlo, if your pi has reasonably light tails, in other words, sub-exponential tails, you will definitely have a spectral gap. So the kinds of things that this assumption rules out is essentially heavy-tailed targets. If you're targeting something like a Cauchy distribution, you would not have a spectral gap. So that's not covered. But provided you have something like sub-exponential or sub-Gaussian, this assumption definitely holds. And in our paper, which we'll hopefully upload next week, we then apply this to indeed logistic regression, which is the main application of quasi-stationary Monte Carlo methods. Okay, so now let me talk about a different kind of perturbation. So the other issue, which I've entirely not discussed in this talk up to now, is how you simulate these killing times. So for example, think about the rescale algorithm I presented a few slides ago. You're running this process forwards in time, and when it's killed, it's reborn. But you have to simulate the killing times. That is absolutely crucial. If you cannot simulate the killing times, you cannot run the algorithm. So how do you simulate the killing times? Well, if the killing rate is uniformly bounded above, which it is in some situations, such as logistic regression, you can straight away just use Poisson thinning, right? If kappa is bounded above by, say, I don't know, 20 or some other constant, you simulate a homogeneous Poisson process of rate 20, and whenever one of those times arrives, you do a kind of acceptance rejection step to decide whether or not it was a true event from kappa. And that's lovely and that's great. However, if kappa is unbounded, simulation is considerably more delicate if you want to do it exactly. And so, for instance, the way it was done in the original scale paper was to use what's called layered Brownian motion. What that basically means is you simulate a hypercube, which kind of constrains your Brownian motion path up to some time interval. And then because you've conditioned essentially your process to live in a compact cube, you then construct a local bound on this cube and then do Poisson thinning on that up to your time interval, which is exact, but very complicated. It will be greatly simplified if instead you simply just chose some threshold m, which you user specified, and you just ran the whole system with a truncated killing rate, right? You just say, okay, maybe the actual killing rate is norm y squared, but we're just going to cut it off at 10 or 20 or something like that, right? Because then if you cut it off at some level, you can then just do Poisson thinning, and it's very straightforward to implement. Okay, but then there are several questions that, of course, you want to ask here. So firstly, unlike what I discussed on the previous slide, this corresponds to an unbounded perturbation. The operator, which is kind of the difference between these killing rates, is an unbounded operator because you've reduced a potentially unbounded killing rate, which is arbitrarily large, down to some finite level. So it's an unbounded operator, although it's still self-adjoint. And secondly, given some m, which is user specified, is there even a quasi-stationary distribution in the first place, right? Clearly, if m is 0, there is no killing and there's no quasi-stationary distribution. If m were really, really small, we might also be worried, is there a quasi-stationary distribution? It's not clear. On the other hand, if m were very, very, very large, it seems intuitive to say that there probably would be, because the region at which your killing is being truncated is probably far in the tails anyway. The process spends very little time there, and so it probably doesn't matter. And so if there is a quasi-stationary distribution pi m, is it close to the original one? So these are some questions we want to answer. And in order to answer them, we just need a tiny bit more notation, so please bear with me. I'm going to write lambda 0 kappa as the bottom of the spectrum of minus the generator. I've put minus the generator so that it becomes positive, and so this is a positive number. I think this is the same as lambda star or lambda, which Emma discussed in her talk. So it's just the bottom of the spectrum is the fundamental eigenvalue. I'm going to call that lambda 0 kappa. Okay, so here's the first result. So provided the truncation level m is above this fundamental eigenvalue, then the truncated system still possesses a unique quasi-stationary distribution pi hat m. So this is good, right? This tells us as long as the truncation is not really small, you know, as long as it's bigger than this lambda naught kappa, there is still something at the bottom of the spectrum. And this makes crucial use of a really nice result of Champagnat and Villemonnet, which discusses essentially the high killing situation. Their result says that provided the killing rate is high, there is a quasi-stationary distribution. And high means it's kind of lim inf in the tails is bigger than the bottom of the spectrum, which is exactly this threshold. Okay, and so we have that. So we're certainly going to assume that m is above this level. So given that, and under some mild technical conditions, which I won't bore you with now, we have the following bound for some c greater than 0. So we can bound the L2 norm between this perturbed quasi-stationary distribution and the true one in L2 by constant times this quantity. So let me just unpack this quantity for you. So kappa is the true unbounded killing rate, which has been cut off at level m. So this term here, and it's the positive part, is essentially the killing we've cut off, right? This is kappa is the bits which are bigger than m, but also shifted by m, positive part. So this is, if you like, the missing killing, but also integrated against pi, which is the true quasi-stationary distribution, squared and then integrated, which I think is quite a natural object because it's exactly the killing we've essentially missed out. So this is the bound you can get to bound the two things. And so in the paper, we consider in detail a 1D Ornstein-Uhlenbeck example, because in this very simple setting, you can do all the calculations and we can get the following explicit bounds where the killing is quadratic, like in the animations I showed earlier. And in fact, we can translate the L2 bound into an L1 bound, where you have a constant c times e to the minus m, where m is the truncation level. And this c is like, I think it's something like 25. So it's nothing too crazy. Okay, so I think I'm actually coming to the end of my talk now. Yes, so this is my last slide. So just to conclude then. So I guess the take-home message from my talk is that quasi-stationary distributions, which kind of naturally arose in the population dynamics literature, kind of in abstract probability theory, they've been used, surprisingly, to perform exact Bayesian inference on tool data sets, as presented in this original paper of Pollack et al. And in my talk today, I focused mostly on a stochastic approximation approach to the computational task of simulation from quasi-stationary distributions. And Divakar Kumar did a lot of the applied work, really applying the algorithm rescale. And in fact, we're actually in the process of re-implementing some of his examples using a new Brownian motion package developed by Louis Aslett in Durham and Murray Pollock. And then towards the end, I also discussed some perturbation theory results for quasi-stationary distributions, which was joined with Daniel Rudolf. And just a few final remarks on future directions and some open problems. So as I mentioned earlier, convergence on non-compact state spaces in full generality, I think, is still an open problem. So that would be great to close that gap. Secondly, I kind of discussed throughout, this kind of interacting particle system and stochastic approximation as if they're fundamentally different. A recent paper of Budiaraja et al. Actually combined the two together, although they just did it, they weren't so interested in MCMC, so they just did it on finite state spaces, I think. It'll be very interesting to see if the two approaches could be combined for Monte Carlo inference problems. And then finally, of course, the topic of this whole meeting is neutron transport equation, which I've not really mentioned at all in my talk. But I hope from Pierre's talk earlier and Emma's presentation, we can clearly see there are links between the kind of algorithms used in that context and in this quasi-stationary context. So I'll be very excited to explore some of those potential connections. And I think that's all I wanted to say. I have a full bibliography for anyone who's interested. I think you have access to my slides. And so with that, I'll just say thank you for listening.
Thank you very much, Andi. Does anyone have any questions? Cecile?
Yes, hi, Andi. Thanks for the nice talk. I thought I would ask you about this last thing you said about combining particles with stochastic approximation. I'm not sure I understand what you mean. I mean, to me, that's the same. I mean, that's the same thing. I mean, I don't understand. Can you just explain a bit more?
Of course, absolutely. That was very quick. So remember how I was saying you can think of a particle approach as kind of sampling in space, where you have a cloud of particles, and when one is dead, you pick from the cloud. I said that stochastic approximation was like sampling in time, right? You have a single trajectory, and when it's killed, you go back in time. Well, why not sample a whole cloud of particles and also sample in space and time, right? So rather than just looking at the present location, why not also look at their past trajectories and sample over that huge object instead? Which is what these people, Bidiraja et al. Did, but only on finite state spaces, I think.
Okay, I see, I understand better. Thanks a lot.
There's a question from Alex.
Hi, thank you. Couple of questions actually quickly. So one was, I mean, I think you sort of swept it under the carpet at some point. You said, so you added this kappa to make everything killing. So sort of early on in the talk, you said you wanted to only have killing in these pictures. I mean, I guess if you didn't have that, you would have, I mean, at least at an intuitive level, this would be like introducing branching, is that right? So yeah, this K here, sorry, yeah, in this result.
Yeah, so again, if we didn't, you're saying if we didn't introduce the killing, there would just be branching? I mean, if there's no killing, it would just be an unkilled Brownian motion trajectory.
So this, yeah, this is in the, I guess this is in the case where you're doing this, the particle picture, right? So if you had branching, you would, I guess, have multiple trajectories, and you would then, but you would then have to do something, some sort of population control to try and sort of keep in order the number. But my guess is you would end up with something like the same stationary distribution in the end. Is that right?
So this particle approach is kind of like what Pierre discussed earlier, right? So you have a cloud of particles which are experiencing killing only. When one of them is killed, you just resample from the cloud. So the number of particles is constant in time.
So you could do the same thing with branching, right? When one branches, you kill one particle at random.
Oh, sure. Yeah. Yeah. You could rephrase it that way. Yeah.
Which I would guess has, I mean, I'm just wondering if there's some reason for only thinking about this as killing, or if there's a...
Right, I see what you mean. Yeah, I've not thought about what it would look like from a branching perspective instead, because of course it wouldn't be the killing rate anymore. It would be something else. That's a really good question. I don't know the answer.
I mean, and I guess in some cases, I mean, well, this K may be very hard to compute, or just, I mean, well, or you have to make it really big, so you get lots and lots of killing events, I would get. I mean, I don't know how problematic this is in practice.
Yeah, I mean, the killing rate has an explicit form, right? And it depends on essentially the properties of your posterior distribution. Yeah, it's very case dependent, I think.
Okay, the other, perhaps the other question I was going to ask is so the rate at which these particles are killed on sorry, maybe step back. Do you have any way of trying to understand when you reach stationarity? I mean, I guess if your landscape is complicated, it may be that you don't yet, I mean, you may have to run the system a long time before you feel like you reach stationarity. I'm wondering how you try and, whether you have any way of...
I mean, this is a fantastic question, right? As in kind of the fundamental question in MCMC as an entire enterprise is how do you know when you've converged, right? There's a whole sub-literature on convergence diagnostics, which range from seriously dubious to probably okay. So the short answer for our kind of quasi-stationary approaches is there currently is not really anything serious I can say. I mean, these algorithms only really developed last year, you know, in all recent years. So we don't have any rigorous convergence diagnostics, unfortunately. And in fact, so another issue I did not mention at all is the fact that especially if you're doing this kind of rescale approach, it basically behaves kind of like a Pollier urn, right? Because it has this rich get richer phenomenon, right? Because you're more likely to visit places you've already visited, which has the horrible practical effect that if you kind of initialize naively and do no tricks, convergence can be absolutely horrendous. Because you imagine if you start in a bad part of the state space where killing is high, you can just kind of be stuck there for a really long time. You have to eventually work your way to the mode and spend a load of time evening out the fact that you started badly. And so there are ways around this, which I don't think I've mentioned. I kind of cryptically said regularization around 0. I mean, one thing you can do is instead of working with mu t, you have, maybe I can actually write on this. Hang on, I think I have the option to annotate in Zoom. If I draw, I hope this works. Oh wait, I don't want to draw straight lines. There we go. Yeah, so instead you work with R over R plus T times some fixed mu naught, and then the rest of the time you do this mu T as I've written here, right? Where this mu zero is some very, very diffuse distribution, maybe just an isotropic Gaussian, and you pick R to be quite large. So it means, you know, if R is like 1,000, for the first 1,000 units of stochastic process time, you're probably just drawing from mu naught, which hopefully means you've scattered enough points around the state space to kind of hit all the modes, right? And then that kind of gives you, it's like the stabilizers on your bike when you're learning to ride a bike. It gives you a bit of guidance at the start before you're let loose to just do your own thing and learn the rest of the distribution. But this is a big issue with these methods, of course. So, yeah.
Great, thank you.
Okay, thank you very much, Andy.